Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we have been going through a section on bondings in solids, which forms a chapter in the paper on physics of materials. And in the section on bondings in solids, we are going through the lecture number 12, which is with the title X-ray diffraction, and the contents of the lecture are continuous and characteristic X-rays, anode target materials, Bragg's law, primary uses of X-rays, and Lobby diffraction. And what is X-ray crystallography? You know, the X-rays which were accidentally discovered by Röntgen can be used for in many areas, but with regard to material science, it can be used to study the arrangement of atoms in a crystal. You take any material, it may be organic material or inorganic material, it may be whatever be the material that you have, the atomic arrangements can be studied using X-rays. A beam of X-rays strikes a crystal and causes the beam of light to spread into many directions. From the angles and intensities of these diffracted beams, a crystallographer can produce a 3-dimensional picture of the density of electrons. I showed some time back the electron density contours in germanium, with the primary objective of telling you how the electrons are preferentially oriented between 2 germanium atoms to show the directional bonding, that is how the electrons are distributed. So, the electronic density distribution, the density of electrons, how they are distributed in crystals, and similarly the arrangement of atoms can be studied using X-rays. This is known as X-ray crystallography broadly. From the electron density, the following features can be determined or obtained: the mean positions of the atoms in the crystal, the chemical bonds, right, and the disorder and various other informations can be obtained from X-ray diffraction studies. Primarily, X-ray diffraction is used to study the arrangement of atoms. By arrangement of atoms, what I mean is, you would have studied in high school that a particular solid is crystallizing in the face centered cubic structure, or another solid crystallizing in the body centered cubic structure, or hexagonal structure, or diamond structure. These crystal structures and the interatomic distances, all these things can be obtained by X-ray diffraction. Not only the positions of atoms, but also the way in which electrons are distributed. No longer you consider the electrons as orbits, revolving in orbits in atoms or in general. So, how the electron density clouds are arranged, right? Electron density contours are seen in order to know the nature of the bonding, whether ionic bonding, covalent bonding, these things can be obtained by X-ray diffraction. Okay. Now, the credit of accidentally observing X-ray diffraction goes to Röntgen. Now, what Röntgen did was to send an electron beam, an accelerated electron beam, and it is made to hit at the target, as I will be showing just now, and from the target or the anode you get X-rays, right. And the nature of the rays which are coming from the target were not known at the time when Röntgen discovered these rays, and as mathematicians do, the unknown quantity is kept as x. You are asked to solve the equations, determine the quantities x and y, or the quantity x is unknown quantity. So, that is the reason why they are called X rays, because the nature of the rays were not known at the time when the discovery was made. It was the year 1895. For that, the first Nobel Prize in physics was awarded to Röntgen in the year 1901. He was honored by the Nobel Prize for physics, and in 1995 the German Post edited a stamp dedicated to Wilhelm Conrad Röntgen. In Germany they are called the Röntgen rays, right, or Röntgen rays, Röntgen rays, and then in general we call it as X rays, right. So, we will read more about X rays and their the properties and the wavelength and things like that, how they are produced and so on. And this is a stamp that was issued by the German Postal Department in 1895 in Bonn. You see the stamp here, maybe one Deutsch mark at that time. Anyway, we will pass on to this is a picture of Röntgen again, and you observe surprising thing was it is told that Röntgen was afraid of the nature of the radiation coming from the target or the X-rays. So, what he did was to catch hold of his wife's hand. So, the easiest thing a scientist can do, instead of testing himself, catching the hand of his wife, and he had the first few photographs can be seen in, if you go to Munich, there is a big museum in Munich where the first few photographs which were taken by Röntgen are displayed, and you see the Mrs. Röntgen's hand, right. You see the ring, right, she is wearing the metallic ring. Similarly, when you take X-ray of mouth, or you got some dental implant, cobalt chromium as I used to have, and you can see the metallic part, right there. So, it is not transparent like okay, it is not like flesh, and it will be the difference between the normal tooth and the metallic system. Similarly, here you see the bone, right, the X-ray will pass through the flesh, right, but not through the bone. You see the bone here, X-ray will pass through the flesh and the bone is seen here, and this is the ring is seen here, the ring which is owned by Mrs. Röntgen. So, the Mrs. Röntgen's hand can be seen. So, this is what was done by Röntgen, the interaction between Röntgen and his wife. Okay. This is a simple X-ray diffraction. You have the electron beam hitting at a target, right, the target, and then you get a diffraction experiment, right, diffracted rings, something like Newton's rings that you have, you would have studied in the school or in the elementary level at a college, the Newton's rings, right. The Newton's rings are due to the wave nature of light. Similarly, the the kind of diffraction that you have, X-rays or waves, a part of the electromagnetic spectrum, and so when they are hitting the target, then you get what is called the diffracted beam, that is the X-ray diffraction that you have. We will see this in a greater detail the time to come. So, what you observe now, a beam of electrons are coming, and they are made to be incident on a target, right. The beam, electron beam is coming and hitting at a target, and now comes the X-rays, and these X-rays you can have on a film or whatever be the thing, right. X-rays can be, in medical field, the X-rays are taken and you have a film in which the X-rays are taken, and or you got other methods of advanced methods for studying the atomic arrangements in solids. So, you got okay, the detectors and so on. So, an accelerating charge radiates electromagnetic radiation, right. Charge gives rise to electromagnetic radiation. Any accelerated charge particle will give rise to, according to electromagnetic theory of Maxwell, any accelerated charge particle will give rise to electromagnetic radiation. So, when you go into the detail, you will be seeing both the characteristic line spectrum and the Bremsstrahlung radiation or the breaking radiation. So, the principle of an X-ray tube is shown here. What you have here is a cathode. You see the cathode here, and you have got an anode here. Okay. The cathode is here, a filament from which the electrons are coming, right. You have the cathode from which upon heating, either thermionic heating, you know, normally use a thermionic heating, and electrons are coming. They are impinging on a target, and you may ask what is the target material. The target material may be copper or molybdenum or iron or cobalt or chromium. Now, these are the common targets used, and now when the electrons are hitting the target, what you observe is the X-rays are coming, right. So, the fast moving electrons, when they hit at a target anode, the anode target may be usually a copper target, right, a copper target, and from the copper target you get the X-ray beam, and you should know when you are talking about X-rays, what are the wavelength region, right, what are the characteristic lines and what is the continuous X-rays, right, the characteristic line spectrum and the continuous spectrum. The continuous spectrum is called the Bremsstrahlung radiation, and so you will be having X-rays, right. So, what you find is you have the high energy beam is hitting, and from the target comes the X-ray beam, right. What is the principle behind the Bremsstrahlung and the characteristic X-ray lines? Now, as I told you, in the target you have got atoms, right, the copper atoms, or in the molybdenum target you will be having molybdenum atoms, right. Now, let us look at one particular atom. It may be a copper atom here, right. You have got a copper atom. As I told you, you have got a fast moving electron, fast incident electron. The electron is coming here, right. It is entering into the atom. You have got a nucleus here. You have got electrons revolving in orbits. So, atom at the anode material, okay, and you have got atom here. Now, what happens is this electron comes here, it interacts with the system, the ejected electron, it gets slowed down and changed in direction. The electron is coming, and this electron is coming here, it does not go straight. What happens is you have the electron giving rise to X-rays, right. You have got the fast moving electron, it interacts with the atom. I will go into the details later, but it interacts with the atom, and in that process what happens is the electron takes a different direction. You have the X-rays coming in this direction, right. Now, when you are talking about X-rays, now we should talk about mainly about the characteristic X-rays, and then we will pass on to X-ray diffraction. For electromagnetic radiation to be diffracted, the spacing of the grating should be of the same order as that of the wavelength. What I would like to tell you is, if a crystal is assumed to be like a grating and you want to have X-ray diffraction, the wavelength of the X-ray beam and the interatomic spacing should be more or less the same order. What is the distance that separates the two atoms in a metal like say strontium? The whole of periodic table, strontium has got the highest interatomic distance. In general, you take all the solids in the periodic table, the distance separating two atoms varies from 2 to 5 angstroms. Maybe strontium is one of the elements which has got the highest interatomic distance, whereas the other solids it will be less than 5 angstroms, right. So, in principle, the interatomic distance in silicon, germanium, copper, molybdenum, everything will be maybe iron, whatever be the thing, all solids will be ranging from 2 to 5 angstroms, right, 2 to 3 angstroms or 2 to 5 angstroms. In crystals, the typical interatomic spacing will be around 2 to 3 angstroms, most of the solids, but strontium is an exception, wherein the X-ray diffraction the distance is very large. Hence, X-rays can be used to study the crystal structure, because the distance are same. You may ask the question, why can't you study the structure, or why can't you study I want to study something what you have in this paper, or I want to see this object. Now, if I want to see this object, the wavelength that is used here should be comparable to the size of the object, right. So, the natural light will be enough to see this object, but on the other hand, when you go to angstrom level, you know the distance that separates the atoms or in the angstrom level. The human eye cannot see objects, whether you can see atoms, you have got atoms in this material, in this plastic or in this paper or in any other material, you have got atoms. Can I see the atoms? The atoms cannot be seen, right. So, you have got the visible region and you have got the infrared, ultraviolet and so on. So, the wavelength of X-rays in general varies from 1 to 100 angstroms. Okay. So, the interatomic distance varies from 1 to 5 angstroms. Now, therefore, if you want to study the interatomic distance in solids, then you have to use X-rays whose wavelength matches with the interatomic distance. Now, therefore, you have to use X-rays. Ordinary light cannot be used to study the atoms, right, atomic arrangements or the structure of in which the atoms are arranged, whether it is body centered cubic or face centered cubic, the atomic arrangements, the distances separating atoms cannot be seen, cannot be studied by ordinary light. Is it whether copper is body centered cubic or face centered cubic or hexagonal close packed, what is the kind of arrangement of atoms that you have? The arrangement of atoms can be seen only by X-rays, and not only the arrangement of atoms and also the interatomic distance, all these can be obtained using X-ray diffraction, using X-rays. So, I will come across what is called a Bragg's law, which will tell you, atoms are arranged in periodically in a regular pattern way in any solid. You have got a plane here, wherein you have got atoms arranged in a periodic manner, and similarly atoms arranged in a periodic manner here, another plane. This is the distance separating the two planes, it is called the interplanar separation, right. The interplanar separation can be obtained from what is called Bragg's law, and again this distance can be measured using X-rays. Okay. So, we again go through the X-ray generation. What exactly happens here? You see here, it is a very interesting animation. You see here, this is a K shell and the L shell, right. Now, you got a atom at the K shell. Now, the fast moving electron that is coming here, and is the target, is one of the atoms in the target, right. It is a copper target or a molybdenum target. Now, what happens? Now, you fast moving electron is coming here, right. Let me wait for some time, right. The electron is coming here. What it does? It throws the electron from the K shell, it throws the electron somewhere, right. The electron goes, and now the K shell is open, right, because the electron has been removed. So, what happens? From the higher state, the electron should come down to the lower state. You have studied the Balmer series, Lyman series, etc., in hydrogen spectrum. So, if an atom is removed, then the other electrons, if the electron is removed, the other electron, the higher energy level should come down, right. So, electron, the K shell is removed, okay. Then the electron, the L shell should fall here, right. You see it again. Now, the electron, the K shell is removed by the incoming fast moving electron, right. Then the electron, the L shell is coming down. The energy difference between this shell and this shell, right, E L and E K, the K shell and the L shell, the energy difference using the Bohr's frequency condition. What is Bohr's frequency condition? E 2 minus E 1 is equal to h nu, right. This is the Bohr's frequency condition. You got one energy level E 2, another energy level E 1. When the electron is jumping from E 2 to E 1, the excess energy will be given out in the form of a photon, right. The difference in energy will come out in the form of a light photon, and the frequency of the photon will be E2 minus E1 will be equal to h nu, right. You got a E2 is the higher energy level, E1 is the lower energy level. You take the hydrogen atom, how do you get Lyman, Balmer, all the other series, Paschen, bracket, Fund series, you know Lyman series, Balmer series, Paschen, bracket, Fund, all the series. What, how do you obtain? You take an electron in the K shell, you excite it, make it to go to the L shell, or still further M shell, N shell and so on. So, whenever electron is jumping from the higher shell to lower shell, from the L shell to the K shell, the electron will be coming down, and when the electron is coming down, a photon will be emitted, right. Similarly, here when there is absence of an electron here, the electron, the L shell will drop to the K shell, right. This is what is happening here. The L shell is dropping to the K shell, giving rise to a photon, right. What is the frequency of the photon? It is governed by the so called Bohr's frequency condition. So, when the electron is jumping from the L shell to the K shell, this electron is coming here, it interacts with the atom, throws the electron in the K shell, there is a vacancy caused in the K shell, that vacancy is filled by the electron in the L shell, the electron in the L shell jumps to the K shell. In this process, a light photon will be coming, right. It is called K alpha quantum, right. A radiation which is called K alpha, right. Similarly, you will be having K beta. K beta is the thing that when the electron is jumping from, this is a K L M. When the electron is knocked off from the K shell, electron from the M shell will go to the K shell, right. From the M shell it goes to the K shell, that is called K beta, right, K beta quantum. Okay. I will show in the slides to come the K alpha radiation and the K beta radiation and the wavelengths, and those wavelengths are used to study the crystal structures. That is the reason why I am telling about the energy levels, the K shell. I showed you the K shell energy, the L shell energy is M shell. So, the energy levels of the electrons in atoms, right. You got the K shell, L shell, M shell and so on, right. And the intensity ratios of K alpha 1, the K alpha 1, this is called the K alpha 2, this radiation coming from this level to this level is called K alpha 2, K beta. The ratio is like this, 10:5:2. So, K alpha 1 will have a higher intensity, right. So, okay, once again I will show the same thing here, the X-rays falling on a target, and this gives rise to X-rays. Okay. Now, you may ask a question, what kind of targets are used, and depending upon the target, let me have the target like molybdenum target, right, impacted by electrons, accelerated by a 35 kilovolt potential, the potential between the cathode and the target or the anode target, right. Then what you observe is the following, you got a white light, right, it is called a Bremsstrahlung radiation, and apart from that you got, this is a continuous spectrum, right. You got continuous spectrum, the wavelength ranging from 0.2 to 1.4 angstroms, the entire big range, the continuous spectrum. Apart from continuous spectrum, you get the lines, this is a K alpha line, this is a white radiation. Apart from this, you got K alpha and K beta, right. Now, the K alpha is the one that is generally used to probe the atomic arrangements in solids. I would like to emphasize this particular feature, the factor, namely this K alpha radiation coming from molybdenum target or copper target is the wavelength that is used to probe or to study the crystal structures. So, you should know the wavelength of the K alpha radiation, because the intensity is high, the K alpha radiation coming from any target, it may be copper target, and how to calculate, how to know the wavelength of the K alpha radiation. Okay, you know, experimentally you can determine, but theoretically also one can try to infer what should be the wavelength of the K alpha radiation. What is K alpha? Jumping from L shell to the K shell. If you know the energy of the K shell and the L shell, then the energy difference will give you h nu, right. From that you can determine the wavelength of the radiation. Now, let me ask you to work out this problem, namely you use the hydrogen atom, you use the maybe the hydrogen atom, what is the energy of the electron in hydrogen atom. Okay. These are the characteristic radiations, right, due to transitions in the atoms. I told you that the K shell, L shell and so on, that give rise to K alpha, K beta is a white radiation, it is called the Bremsstrahlung radiation. Okay. Then again I will explain the incoming electron, it interacts and the electron is dislodged, this electron is K shell electron is dislodged from the K shell, and so when the electron is dislodged, the electron in the L shell drops to the K shell, it gives rise to K alpha radiation, whereas the electron is jumping from the M shell to the K shell, it gives rise to K beta radiation, right, K beta X-ray. So, K alpha and K beta are the two important characteristic line spectra that you get in copper target or molybdenum target, and one generally makes use of the K alpha radiation to probe or to study the crystal structures. Let me now ask you as to how you can calculate the, okay, this is a thing that the animation that shows. Now, what are the characteristics of X-rays? A high energy electron or photon interacts with the electrons in the target anode atoms. As I told you, an inner orbital electron is displaced, removed, the outer electron jumps, okay, that gives rise to K alpha radiation, right. If an L shell electron is replacing a K shell electron coming from L shell, it is dropping to K shell, then you get a K alpha radiation. On the other hand, if the electron in the M shell is coming to the K shell, you get the K beta radiation that as I showed you just now. Then now comes the targets which are generally used, and what are the advantages and disadvantages of various targets. I will not go into the greater detail of the advantages and disadvantages, but mainly let us try to emphasize the materials used, namely the targets are made up of either chromium or iron or cobalt, and if you want to probe a material containing more of iron. So, in this case the most useful this iron target is being used when you want to study the iron rich materials. Iron rich materials can be studied using a iron target, right. So, the target material is an important feature. Now, the radiation coming in the case of the K alpha 1, the wavelength that is emitted during the process which I described earlier. In the case of chromium, it is 2.29 angstroms. In the case of this one is 1.936 angstroms. In the case of cobalt, it is 1.789 angstrom. But more than these three targets, the most important targets are copper and molybdenum. The most widely used target is copper and molybdenum. Now, most of you know what is the wavelength of the, should know or should remember, the people who are doing X-ray diffraction studies should by heart or should remember this particular value 1.541 angstrom. What is 1.541 angstrom? That is the wavelength of the K alpha radiation or K alpha 1 radiation that is usually used for probing, for studying the crystal structures of most of the materials. Mostly people make use of this copper target. Best overall for the anode target is the best one, best overall for most inorganic materials. For shorter wavelength molybdenum target, shorter wavelength good for small unit cells, particularly metal alloys, right. You make use of molybdenum target, right. And now we will wind up this lecture. We will go to the summary part, and let me summarize as to what I have done today. For electromagnetic radiation to be diffracted by solids, the wavelength should be in the range 2 to 3 angstroms, or in other words, X-rays ought to be used to study the crystal structures. When a high energy electron knocks off the electron in the K shell, then the electron in the L shell will jump into the K shell, giving rise to what is called the K alpha radiation. The targets which are commonly used are copper, molybdenum, iron, cobalt and chromium. These are the normally used targets. Okay. And you get the K alpha radiation depending upon the K alpha or K beta depending upon the electron which is falling into the K shell, whether from L shell or the M shell. The important anode targets I mentioned just now. Then the Bragg's law is of immense use as it gives the lattice parameters. Now, we will pass on to the question session. Question number 1, what are characteristic X-rays? Number 2, how will you calculate the wavelength of K alpha radiation? Question number 3, how is K alpha radiation produced? What is the range of lattice parameters in solids? With this we come to the end of lecture 12, and in the lectures to come we will go through Bragg's law, the Laue pattern and so on, the other things which are to be covered. Thank you.